In the beginning, there was darkness, a silence so profound it could swallow thought itself. No planets, no sun, not even the faintest glimmer of dust. The universe, newly born and unfathomably vast, was ruled by clouds of gas and whispers of gravity. The place that would one day cradle our solar system was, by all reckoning, indistinguishable from the infinite sea of cosmic dust. Yet within that primordial emptiness, the seeds of stars and worlds already waited, hidden in the cold embrace of a nebula. Amid the grand tapestry of the Milky Way, one such nebula drifted, an immense, swirling cloud of hydrogen, helium, and heavier elements, the silent gifts of long-dead stars. It was a colossal structure, perhaps 1 to 3 light-years across, its mass measured in tens of thousands of suns. Across its breadth, atoms collided, merged, and parted ways, guided by the subtle hands of turbulence and magnetic fields. The nebula was restless, churned by shock waves from distant supernovae, sculpted by the pressure of nearby starlight, forever on the verge of collapse and creation. The moment of transformation was neither sudden nor gentle. Over millions of years, gravity pulled denser knots of matter inward, causing them to grow heavier still. A subtle instability, perhaps triggered by the ripple of a passing star or the echo of an ancient explosion, tipped the balance. The densest region began to contract, heating as it shrank, spinning as it tightened, conserving the angular momentum that every atom carried from the nebula's slow rotation. What had been a cloud became a disk, flattened by the inexorable mathematics of motion. The center blazed brighter, a star in the making. Around it, a whirling disk of dust and gas, a cosmic carousel, marked the birth of our solar system. At the heart of this disk, where pressures and temperatures soared, hydrogen atoms fused into helium, releasing light and heat. The sun ignited, not all at once, but gradually, as the core grew dense enough to sustain nuclear fusion. The sun's birth was violent. Its solar wind, an unending stream of charged particles, began to sweep outward, blowing away the lighter gases from the inner disk. The temperature gradient across the disk was dramatic. At the center, searing heat. Farther out, a realm so cold that water, methane, and ammonia froze to ice. In these differences, the architecture of the future solar system was written. Within the disk, grains of dust, each no larger than the motes that dance in sunbeams, began a slow, miraculous journey. Electrostatic forces pulled them together, forming clumps, then pebbles, then rocks. Over hundreds of thousands of years, these fragments collided and merged, sometimes shattering, sometimes sticking, guided by the subtle choreography of chance and physics. Some grew large enough to exert their own gravity, attracting still more material. These planetesimals, ranging from mere kilometers to hundreds of kilometers across, became the building blocks of planets. The early solar system was a place of chaos and violence. Collisions were constant, shaping, destroying, and remaking the protoplanets. Some impacts released energies comparable to trillions of megatons of TNT, far beyond the might of all the nuclear weapons ever built. The formation of the Earth-Moon system itself was likely the result of such a cataclysm. A Mars-sized body, Theia, struck the young Earth, vaporizing itself and much of Earth's crust. The debris thrown into orbit coalesced over millennia into our moon. Farther from the sun, beyond the so-called frost line, the rules changed. Here, ices were abundant, allowing protoplanetary cores to grow larger, accreting gas from the surrounding disk. These giants, Jupiter, Saturn, Uranus, Neptune, became titans, their masses dwarfing those of the terrestrial worlds. Jupiter alone contains more than twice the mass of all the other planets combined, its gravitational might shaping the orbits of asteroids, comets, and even the fates of smaller planets. Between the orbits of Mars and Jupiter, the formation of a planet was thwarted by Jupiter's gravity. Instead, countless rocky fragments, asteroids, remained, many of them unchanged since the dawn of the solar system. The asteroid belt is a museum of primordial history, where objects like Vesta and Ceres offer clues to the processes that forged our world. Some asteroids are so massive that their impact would unleash energies millions of times greater than the largest nuclear detonations, reshaping planetary surfaces and, in some cases, altering the course of evolution itself. Beyond Neptune, in the distant reaches of the Kuiper Belt, icy bodies drift in shadow. Pluto, Eris, Haumea, Make, dwarf planets and countless smaller worlds, relics of formation, each orbiting the Sun on paths shaped by ancient migrations of the giant planets. Here, comets wait in cold storage, their tails stretching for millions of kilometers when they venture inward, painting the sky with ephemeral light. The solar system's birth was not a solitary event. Across the galaxy, stars and planets emerge in similar fashion, shaped by the same laws of physics that governed our own formation. Yet the details, timing, composition, violence, and chance render every solar system unique. In our own, the balance of elements, the placement of planets, the presence of water, and the gentle warmth of a stable sun have conspired to make Earth a cradle of life. But this outcome was far from inevitable. It was the result of countless random events, each echoing across deep time. The story of the solar system is written in stone and ice, in magnetic fields and planetary atmospheres, in the scars of craters and the subtle chemistry of meteorites. Every planet, every moon, every fragment of rock carries a chapter of this shared history. The oldest meteorites, called chondrites, are time capsules. Their isotopic ratios reveal that the solar system formed 567 billion years ago, give or take a few million. These ancient stones predate the Earth itself, bearing witness to the earliest moments of planetary assembly. Consider Jupiter's Great Red Spot, a storm larger than Earth, raging for more than 3 centuries. Or Saturn's rings, stretching hundreds of thousands of kilometers, yet only a few meters thick, composed of countless icy fragments. Or the Oort Cloud, a hypothetical sphere of icy bodies extending perhaps a light year from the Sun, the birthplace of comets whose journeys last millions of years. The solar system's scale defies imagination. The distance from the Sun to Neptune is nearly 4.5 billion kilometers, yet the influence of the Sun's gravity stretches much farther, binding distant objects in orbits that take millennia to complete. The formation of the solar system is not merely a tale of mechanics and chemistry. It is a story of transformation, of emergence from chaos into order, of violence giving way to stability, and of the slow coalescence of dust into worlds. It is a story written in the language of physics, but experienced by every creature that has gazed upward and wondered at the night sky. In the centuries since humanity first sought to understand the cosmos, our questions have grown more precise, our tools more powerful. Galileo's telescope, Newton's equations, Laplace's nebular hypothesis, each added a layer of understanding. By the late 20th century, with the advent of space exploration, our knowledge expanded exponentially. The Voyager probes, launched in 1977, journeyed past the outer planets, sending back images and data that revealed the diversity and grandeur of our celestial neighborhood. Voyager 1, now more than 23 billion kilometers from Earth, carries with it the story of our origins, etched onto a golden record, adrift among the stars. Modern astronomy has allowed us to witness the birth of other solar systems. The Atacama Large Millimeter Submillimeter Array, ALMA, perched high in the Chilean Andes, has imaged protoplanetary disks around young stars, revealing gaps and rings carved by forming planets. In the Orion Nebula, the Hubble Space Telescope has captured the glow of infant stars still shrouded in gas and dust, their future planetary systems hidden from view. These observations confirm that the processes that shaped our solar system are universal, yet endlessly varied in their outcomes. The solar system is not a static place. Its architecture has changed over billions of years, sculpted by gravitational resonances, planetary migrations, and chaotic encounters. The NICE model, proposed in the early 2000s by a team of French and Italian astronomers, suggests that the giant planets once orbited closer together, their interactions scattering asteroids and comets throughout the solar system. Such migrations may have delivered water and organic molecules to the young Earth, setting the stage for life to emerge. The story of water on Earth is itself a cosmic odyssey. Did our oceans come from the solar nebula, from icy comets, or from hydrated minerals and asteroids? Measurements of deuterium to hydrogen ratios in comets and meteorites have revealed a complex history, with contributions from multiple sources. The presence of water on the Moon, Mars, and the icy moons of Jupiter and Saturn hints at a solar system richer in potential habitats than once imagined. Every planet and moon carries scars of ancient impacts. The craters on Mercury and the highlands of the Moon record a period known as the Late Heavy Bombardment, around 4 billion years ago, when the inner solar system was pummeled by debris. Some impacts were so powerful that they melted entire regions of planetary crust, vaporized oceans, and altered the chemistry of atmospheres. The Chicxulub impact, 66 million years ago, released energy equivalent to 100 trillion tons of TNT, enough to drive the mass extinction that ended the reign of the dinosaurs and opened the way for mammals and eventually humans to flourish. The solar system is also a place of ongoing dynamism. Volcanoes erupt on Io, the innermost moon of Jupiter, spewing sulfur hundreds of kilometers into space. Geysers of water and organic molecules jet from the frozen crust of Enceladus, hinting at a subsurface ocean warmed by tidal forces. Mars, once home to rivers and lakes, now wears the scars of dust storms that can engulf the planet for months. Each world is a laboratory, a record of the processes that shape planets everywhere. The scale of the solar system invites both awe and humility. The Sun contains 99.8% of all the mass in the solar system, its fusion-powered heart shining with the brightness of 3.8x to 1026 watts, enough energy to power every human civilization for trillions of years. Jupiter's magnetic field is 20,000 times stronger than Earth's, trapping charged particles in radiation belts that could fry electronics in minutes. Saturn's rings, if stretched end to end, would reach nearly from the Earth to the Moon. The largest known volcano, Olympus Mons on Mars, rises 22 kilometers above the plains, 2.5 times the height of Mount Everest, its base sprawling across an area the size of Arizona. Yet amid these grand scales, the solar system is fragile. Earth's environment depends on a delicate balance: distance from the Sun, atmospheric composition, magnetic shielding, and the gravitational influence of other worlds. Small changes over millions of years can shift climates, reshape continents, and drive the evolution of life. The search for other Earths, planets orbiting distant stars, reminds us both of our uniqueness and our kinship with the cosmos. The boundaries of the solar system are not easily defined. The heliopause, where the solar wind yields to the interstellar medium, lies some 120 astronomical units from the Sun, about 18 billion kilometers. Beyond this, the Oort Cloud may extend as far as 100,000 astronomical units, or 1.5 light-years. A single comet from this distant region, like Hale-Bopp, can display a tail stretching 100 million kilometers, its icy nucleus vaporizing as it nears the Sun, releasing more water each second than flows over Niagara Falls. Throughout history, comets have been omens and mysteries, heralds of change, objects of fear and wonder. The impact of Comet Shoemaker-Levy 9 on Jupiter in 1994 released energies equivalent to 6 million megatons of TNT, carving scars the size of Earth into the giant planet's atmosphere. Such events remind us that the solar system remains a place of unpredictable drama, where ancient forces still shape the present. The exploration of our solar system is one of humanity's greatest achievements. The Apollo missions carried humans to the Moon, allowing us to touch another world and bring back samples that illuminated the history of both Moon and Earth. The robotic explorers, Spirit and Opportunity on Mars, Cassini at Saturn, New Horizons at Pluto, have transformed our understanding, revealing landscapes and processes stranger than we ever imagined. Curiosity and Perseverance, the latest Mars rovers, search for signs of ancient life in the red planet's rocks, drilling and analyzing with instruments more sensitive than any before. The European Space Agency's Rosetta mission landed on Comet 67P Churyumov-Gerasimenko, discovering organic molecules and reshaping our theories about the delivery of life's building blocks. The James Webb Space Telescope, launched in 2021, peers into the atmospheres of exoplanets and the dusty nurseries of new stars, seeking the fingerprints of water, methane, and perhaps life itself. The solar system is a story in progress. New discoveries arrive almost daily. Subsurface oceans on icy moons, possible plumes on Venus, strange interstellar visitors like Oumuamua, an object whose speed and trajectory mark it as a wanderer from another star. Each discovery challenges our assumptions, expanding the boundaries of possibility. The chemistry of the solar system is a record of cosmic alchemy. The elements that form planets, moons, and life were forged in the hearts of earlier stars, scattered by supernovae, assembled into clouds and woven into new generations of worlds. The iron in your blood, the calcium in your bones, the carbon in every living thing, all were born in ancient stars, their atoms now part of a grand cycle that spans the galaxy. The solar system is a clock, its rhythm set by gravity and motion. The Earth's axial tilt gives us seasons. The resonances of Jupiter shepherd asteroids and comets. The cycles of ice ages and mass extinctions are written in the slow dance of planets and the steady drift of continents. Time itself is measured by the motions of worlds, the ticking of atomic clocks, the decay of radioactive isotopes, and the light of distant stars. Beneath the surface of our own world, the memory of the solar system's birth is encoded in isotopic ratios, mineral grains, and the slow accumulation of sediment. The oldest rocks on Earth, in Western Australia and Greenland, are more than 4 billion years old. Yet even they are younger than some meteorites, which preserve the record of the solar system's earliest moments. Zircon crystals, trapped in these ancient stones, contain hints of the first oceans, the first continents, the first stirrings of life. The solar system is also a crucible of extremes. Mercury's surface swings from 430 degrees Celsius in sunlight to 180 degrees Celsius in darkness. The winds of Neptune howl at 2,100 kilometers per hour, faster than the speed of sound on Earth. Venus's atmosphere, thick with carbon dioxide, crushes spacecraft and bakes the surface to 460 degrees, hot enough to melt lead. On Titan, Saturn's largest moon, methane rains fill lakes and rivers, sculpting landscapes beneath a golden haze. The solar system is a place of mystery, where questions linger. Why is Uranus tilted on its side? What lies beneath the ice of Europa and Enceladus? How did Mars lose its atmosphere and water? Could life exist elsewhere, in the clouds of Venus, the oceans of Europa, the depths of Titan, or beneath the surface of Mars? These questions drive exploration, inspire new missions, and challenge our understanding of life's potential. The vast distances between worlds are both a barrier and an invitation. The fastest spacecraft ever launched, NASA's Parker Solar Probe, travels at 700,000 kilometers per hour. Yet it would take more than 6,000 years to reach the nearest star. Light itself, moving at 300,000 kilometers per second, takes 8 minutes to reach Earth from the Sun, and more than 4 hours to reach Neptune. The scale of the solar system humbles our ambitions yet fuels our dreams. The solar system is a family of worlds, each unique, each shaped by common origins and divergent histories. The rocky planets, Mercury, Venus, Earth, Mars, bear the scars of early violence, the legacy of impacts, volcanism, and tectonics. The gas giants, Jupiter and Saturn, are worlds of storms and magnetic fields, their moons rich in diversity and potential. The ice giants, Uranus and Neptune, are mysteries still, their faint rings and distant moons only partly explored. The story of the solar system is a story of change. Planets migrate, atmospheres evolve, moons shift and shatter, comets arrive and depart. The sun itself is not eternal. 5 billion years from now, it will exhaust its hydrogen fuel, swell into a red giant, and eventually shed its outer layers, leaving behind a white dwarf. The planets will be cast adrift, their fates uncertain, their histories embedded in the cold silence of space. Yet amid this cosmic drama, life has emerged. On a small blue planet orbiting an ordinary star, The conditions that make Earth habitable are the result of countless coincidences and contingencies. A stable orbit, a protective magnetic field, an atmosphere rich in oxygen, water in all its forms, and the gentle warmth of the sun. Life, in turn, has shaped the planet, modifying the atmosphere, sculpting the continents, and, in the case of humanity, reaching out to touch other worlds. Our solar system is both a destination and a starting point. Missions are planned to return samples from Mars, probe the oceans of Europa and Enceladus, study the atmosphere of Titan, and even visit the metallic asteroid Psyche. The search for life, the quest to understand our origins, the drive to explore, these are the legacies of the solar system's birth, written into the code of every living thing. The solar system is a reminder of our place in the universe, small, fragile, and temporary, yet capable of wonder, discovery, and creation. The dust that formed the planets is the dust of ancient stars. The atoms that make us are the atoms that built the worlds. The story of the solar system is our story, written across billions of years, inscribed in the rocks, the ice, the winds, and the light of the sun. To gaze up at the night sky is to look back in time, to see the light of ancient stars, the ghosts of comets, the shadows of planets. It is to remember that we are part of a vast and ongoing story, one whose end is not yet written, whose possibilities are as infinite as the cosmos itself. In the fullness of time, the solar system will evolve and change. The sun will fade, the planets will drift, the story will continue elsewhere. But for now, we are here, children of dust and light, heirs to a legacy of creation and destruction, explorers on the shores of a cosmic ocean. The solar system is our home, our past, our future, a place of wonder, beauty, and endless possibility. And so, as we stand on this small world and look outward, we remember. The solar system began in darkness and dust, forged by gravity and chance, shaped by violence and time. From those beginnings emerged the sun, the planets, the moons, and ultimately ourselves, a testament to the power of transformation, the persistence of curiosity, and the unbroken chain of creation that links us to the stars.